Okay, so let's consider an optical cavity here, a single mode optical cavity for simplicity, and let's think that one of the mirrors in the optical cavity is a nano or a micro mirror, and the mirror can move. So once you put a field inside the cavity, then this field is going to exert radiation force on this movable mirror. As a result, the mirror experiences the displacement, and the simplest effect of this displacement would be to change the frequency of the cavity. And the change in the frequency of the cavity is dependent on the displacement of this mirror. So this is basically the optomechanical interaction between the optical degrees of freedom and the mechanical degrees of freedom, and this interaction is leading to many interesting effects. It's providing us a new class of systems for studying nonlinear optical effects, for studying quantum optical effects. For studying quantum optical effects, the cooling of these nanomechanical systems is important, and we will discuss how the cooling can be achieved. Now in future, one would like to study cases where a single photon is sufficient for causing a very effective optomechanical interaction. Let me quickly show it to you how the Hamiltonian for the optomechanical interaction looks like. As I said that the radiation pressure gives you a displacement of this mirror which causes the change in the frequency. So the Hamiltonian effectively has this form. This seems to be dying. Yeah? The Hamiltonian has this form. This is the cavity part, and this is the mirror part. Note the x dependent of this frequency, and since this mirror happens to be at the node of the cavity, so you can approximate this interaction by an interaction of, thank you. Yeah. So if you approximate this change in the frequency by the linear term, then you get an optomechanical interaction term of this kind. So this is the number of photons in the cavity, and here is the displacement of the mirror written in terms of the standard harmonic oscillator operator. In addition, we need to couple the system to the outside field, so we can add the outside driving fields to the system. Plus, we need to take into account the dissipative processes in the cavity and the mirror, including the thermal noise. So some of the early optomechanical systems involved, for example, the silica microsphere, where the microsphere acts like a resonator, and the optical mode was the whispering gallery mode of the silica microsphere, and the mechanical mode was the radial breathing mode. Espelmeyer designed a optomechanical system where he replaced one of the mirrors by a strongly reflective micro mirror. Harris at Yale, he had a system where you used a silicon nitride membrane on a silicon chip. Over the years, many different kind of optomechanical systems have been designed and many different kind of studies have been made. Some of the groups, main groups in the area are listed here. Is the cavity mode which is driven by an outside laser field. Okay. There are other kind of optomechanical interactions. The one which I talked just now involved the changes in the frequency of the cavity, giving rise to optomechanical interaction. It's also possible to have the reactive optomechanical interaction, and in this case the leakage out becomes dependent on the displacement. So again, this is one of the reactive optomechanical systems. It's a micro disc coupled to a nano waveguide. There are several electromechanical analogs of these reactive optomechanical systems. You can also have a Sagnac interferometer with a beam splitter here whose reflectivity is not 50%. Then you can realize a reactive optomechanical interaction. But I would in this talk mostly be concentrating on the dispersive optomechanical interactions. Okay. So I'm going to tell you a variety of coherent effects which are possible in these optomechanical systems, and this would include electromagnetically induced transparency, electromagnetically induced absorption, mode conversion. You can convert an optical mode to a microwave and vice versa. I'll tell you how you can do a Ramsey spectroscopy by a coherent phonon. And once you have the EIT, you can do memory and the storage applications using these systems. You can also produce transducers and photon routers. So those were the coherent effects. You can also do a large number of quantum optical studies, and now you are dealing with these nanomirrors or micromirrors. So you are basically looking at quantum optical effects at macroscopic scale. So one can think of a variety of these effects following what one does in quantum optics, and right now this is kind of a wish list. All right, so let's look at first the coherent effects. So we have seen that the optomechanical interaction has this form. This is the displacement of the mirror. These are the fields in the cavity, and this reminds us of a nonlinear interaction or nonlinear optical interaction. It's a parametric interaction. So if you think of this is like a three-wave interaction involving two optical waves and one phonon. Phonon is associated with the displacement of the mirror. So this kind of interaction allows you these two distinct possibilities. So you can come in with a red detuned photon, and let us say you have the mirror excitation. Then these two can combine and produce a photon at the higher frequency, omega p, or you can have a down conversion. You can have a blue detuned photon, and this can get converted into a photon at the cavity frequency, and produce a phonon. So this is a down conversion process in the blue detuned case, and you can even generate these two from the vacuum. So you can have spontaneously produce this photon and this phonon. And in the applications, we are going to choose this frequency to be close to the resonator frequency. So these type of processes, these are the in nonlinear optical language you would call as the Chi2 processes. We also know from nonlinear optics that you can combine Chi2 twice and produce four-way mixing processes. So starting from a pump at omega L, you can produce Stokes, anti-Stokes, and all the higher order ones. So look at this one, for example, that you come in with a red detuned pump, and you come in with a probe which is close to the cavity frequency. Now these two can be combined by the optomechanical interaction and can produce a coherent phonon. Once you produce this coherent phonon, you can combine with this omega L and you produce omega P. So both are Chi2 processes, but if you look at this one, a combination of these two amounts to a Chi3 process. Okay, the optomechanical interaction itself can be used for cooling. If you look at this process, you come in with a red detuned laser, and this can be a thermal phonon. So you combine these two and produce a cavity photon, and this cavity photon leaks out quickly from the cavity. So that means you have removed a thermal quanta by this process, and these people have used for cooling these nanomirrors, micro mirrors. Just to give an example, if the mechanical frequency is like 100 megahertz, and if you are at a temperature like 1.5 K, then the mean number of phonons would be like 300. So clearly, if you want to do any quantum optical effects, you have to get rid of these thermal phonons. Okay, so for the calculation of the cooling effect, one has to do a full quantum mechanical calculation, and I had mentioned in the beginning that one has to add the effect of the driving term, effect of the dissipation terms. So these are the dissipation terms in the mirror, and this is in the cavity, and then these equations have to be supplemented by the corresponding quantum Langevin terms. And for the mirror, you have this, which includes the Brownian noise contribution. So that's a temperature dependent contribution. And if you do the calculations, then what we find is now the effective temperature. So you use some of these parameters from the known experiments, and you start at a temperature like 1 Kelvin, and you look at what is the effective temperature produced by this sideband cooling process for different values of the pumping power, and you find that you can reach temperatures of this order 10 millikelvin. Of course, eventually there is a limit here because some of the nonlinear effects start entering here. So by increasing the power, you cannot indefinitely have lower and lower temperatures. So again, in some of the early experiments, what people demonstrated. So in this case, starting at a temperature 1.4 K, they got to about 200 millikelvin. Another experiment, this was a superconducting experiment, starting with a temperature like 20 millikelvin, and they really got to the ground state of the system. Okay, so I come back to the coherent effects now, and first I like to describe the EIT in optomechanics, and so you know, having worked in the EIT in the past, we knew what to look for. We knew how to look for the interfering processes in order to produce EIT. So if the cavity were empty and you come in with a probe field of the frequency omega p, then this field is transmitted. This is one of the possible processes in the cavity. On the other hand, the optomechanical interaction that I described to you. So you come in with a pump and this probe. You combine these two to produce a coherent phonon. This coherent phonon in turn interacts with the pump and produces this probe photon. So it's possible that this process and this process can interfere with each other, and this can give rise to EIT. And if you do the calculations, you indeed find it. So you find this is the output from the cavity, one of the quadratures of the output, and look at this this black curve. That's the signature of EIT, and the width of this EIT hole, it depends on the pumping power, and you can obtain how much is this width of the hole, and it's related to this parameter, which is called the cooperativity parameter. Kappa, gamma are the dissipation rates of the cavity and the mirror, and G is an effective optomechanical coupling constant. So this is the single photon coupling constant, and this is the strength of the driving field. Okay, so this I already explained to you that how in optomechanical systems there are two processes which interfere with each other, leading to EIT. You can also look at this EIT in terms of the rest states of the optomechanical system, and we look at the rest state including the dissipative processes. And if you include the dissipative processes, look at the complex modes, their real and imaginary parts, then these curves show that there are two distinct regimes. One is this regime where the real part of the mode frequency is splits, and the other one is this regime where the imaginary part of the mode frequency splits. And in the past we have termed this regime as the lifetime splitting. In a recent experimental work just appeared in Nature Communications. Sorry. So I was saying that that in a recent work, Heinz group, and even though they have studied the cavity QED system, they have reported a lot of experimental results in this regime. That is how I look at it. Okay, Rabi splitting are the Atlas Towns splitting. Okay, so fortunately on EIT there have been many experiments after our original proposal, and these days anybody who builds an optomechanical system, EIT is one of the first thing they check on in their system. So one of the original first experiments, unfortunately I don't have a slide, was done by Kippenberg, and the next one was done by Painter's group, and you can see the EIT profiles. In this case, this detuning parameter has been chosen to be equal to the mechanical frequency, and the curve that I showed you corresponded to this case. There are also data for other values of the detunings, and this hole is plotted here for different pump powers, and one can see that the width of this hole is proportional to the control power or the pump power as the theory predicts. So this is another experiment on EIT, and this is done in silicon nitride microdisc optomechanical resonators. You see this nice EIT peak here. On this side, this is the mechanical profile, depending on which mode you select there. And you can again see that this dependence of the bit on the level of the power of the pumping field. Yeah, there are similar results on EIT in graphene resonators. So this group in Holland, they combine graphene mechanical resonators with the electromechanical systems. Okay, in EIT in the atomic system, we know that the atomic coherence is very important, and so for our optomechanical systems, we generate coherent phonons, and so this is the phonon amplitude plotted as a function of the frequency relative to the mechanical frequency, and you see a very nice peak at this mechanical frequency, telling us that phonons are coherently generated. Okay, other applications, there are other systems like Beryllium optomechanics, and Beryllium optomechanics, the experimental work pioneered by Talman's group. The origin of the optomechanical interaction is somewhat different here for the Beryllium optomechanics, is due to the electrorestriction, which means change in the electromagnetic response due to sound waves, and so the dielectric function becomes a function of the density of the medium. And so if you look at this electrorestriction as the origin of the optomechanical interaction, you can again obtain the fundamental equations involving three waves, two optical waves and one phonon or the sound wave, with a coupling constant which is determined by the overlap of these optical mode functions and the sound wave mode function, and this gamma E is related to the electrorestriction. And so once you have these kind of equations, they is similar in nature to what I discussed earlier. So whatever we discussed earlier is applicable to this system, and these two they studied EIT in these systems, So they're called billion scattering induced transparency. And in billion optomechanics, in order to have very good optomechanical coupling, you choose modes which are two modes of the resonator. So both pump and the probe are chosen such that they coincide with one of the mode of the resonator. And this difference is just the frequency of the sound wave there. And so what you see here in the transmission, you see this EIT or the transparency P. And just a prediction of those three coupled equations from the previous slide. So this was reported by two different groups, and Kim et al. They also reported probe time delay, slow light, and things like that, which are all associated with the EIT. Okay, so we also looked at in one of the theoretical papers, the optomechanical interaction in a superfluid, and the idea to look at in a superfluid was that because such systems have very low friction, almost zero friction, and so advantageous for the optomechanical interaction. And so if you look at the basic equations, you have the equations for the fluid. So T is the stress tensor for the fluid, and you add a term involving the interaction with the electromagnetic field. So this contribution is basically the divergence of the stress tensor corresponding to the electromagnetic field. And and the equation for the electromagnetic field, you have modification. This epsilon depends on the density. So we have these two coupled equations which describe to you the optomechanical interaction in superfluid. And so you make a density expansion and also quantize everything. Then in leading order, you can write a Hamiltonian in this form. I think I added an extra A somewhere. Yeah. Density of the superfluid. Superfluid, which is contained in a cavity. So you look at the density changes in the superfluid, and these density changes in the superfluid without this term is just the equation for the superfluid, you know. This is the divergence of T, which is related to the pressure in the fluid, okay. And to this, we now add a term corresponding to the interaction with the electromagnetic field. And so I need to put in the stress tensor for the electromagnetic field, okay. And then this one, of course, is the standard equation, except you write the dielectric, optical property of the superfluid in terms of its density. So, and I mean, these are very complicated equations, and so you can simplify and you can do a leading order expansion. The rho naught is the equilibrium density, and then a perturbation due to the applied electromagnetic field, and you can develop then the Hamiltonian description of these two equations after quantization and all that. So you get optomechanical interaction, and with a coupling constant which is estimated here. There, this parameter G1 is related to the derivative of this optical property and this is the sound velocity, this is the equilibrium density, and so on. This parameter is known from experiments in the literature, and so you can estimate this optomechanical parameter, and we estimated this parameter for a fiber cavity to be of this order. So it's a fairly large optomechanical interaction in this fiber cavity, and this recent experiment which Harris reported, he reports this value of the optomechanical interaction. So he does report very large value of the optomechanical interaction in these superfluids. So once you have a reasonable value of G, this optomechanical interaction, then the rest follows. Okay. So I now like to describe to you some of the applications of these coherent phonons which are generated in the optomechanical system, and one possibility to demonstrate, because we wanted to demonstrate that the phonons which are generated are indeed coherent. So in order to demonstrate the coherence property of these phonons, you can do Ramsey spectroscopy. And let me quickly remind you what Ramsey spectroscopy is. So if you think that you send an atom through fields which are applied in two different zones which are separated by this time interval, and then you can look at the excited state population here as a function of this this duration, or as a function of the resonance frequency. But you find that in this setup, the excitation probability looks like this, whereas if you had used single excitation zone, then the excitation probability would have looked like this. And so these are the Ramsey fringes, and Ramsey fringes have been known to provide one with a high resolution method. And the Ramsey interferometer is an interferometer as illustrated here, that the atom can be excited either by this field, or the atom can be excited by this field. So you have two paths for excitation, and these two paths can interfere with each other, and this gives rise to Ramsey fringes. Okay. So how about with the coherent phonons, or if we want to test that the generated phonons are coherent? So we can do optomechanical interaction following Ramsey method in two different zones. Optomechanical interaction in this zone, and then optomechanical interaction in this zone. And what we do is the following: in this zone, so coherent phonons are generated, as well as the probe photon is generated, and we choose this time t in such a way that the kappa times t is much larger than 1, whereas gamma times t is smaller than 1. And typically in optomechanical systems, gamma by kappa is about 10 to the power 4, or even smaller, or even large. I'm sorry, kappa by gamma is 10 to the power 4 or even larger. So this is not difficult to do. So what will happen now, that by the time you come to this zone, this would have gone, whereas these phonons would have survived and would have reached this region. And now in this other region, we have the second optomechanical interaction, and the second optomechanical interaction, you produce this probe photon, and these phonons which came from this region would also produce these probe photons. And so what you see that we have two paths. These photons, these probe photons are produced either by the optomechanical interaction in this region or by the coherent photons which were produced in this region. And so if we observe in the signal here fringes, then these fringes would be evidence that we have produced coherent photons in the optomechanical interaction. So that's how MJ would work with the coherent photons. And I asked a friend in Oregon, Wong, whether they can do this experiment, and they did the experiment. Of course, when you do the experiment, you have to test everything. You have to test the properties of your optical mode. You have to test the properties of your mechanical mode, and so here are the experimental results on the Ramsey interferometry with photons, and so it demonstrates clearly that the generated photons are coherent. Okay, so we can use these coherent photons in many different ways. For example, we can do a mode conversion. So this is possible if you think of a double cavity arrangement. So you can think of a cavity here and couple to another cavity here. This could be in a different frequency domain. So this could be an electromechanical cavity. This is an optomechanical system here. And so basically you produce these coherent photons, and these coherent photons combine with the pump here to produce a signal on the other side. Okay, so the result of the calculation, we can look at the left cavity output. We can look at the right cavity output, and what happens under rather these stringent conditions. These conditions are rather stringent. So, but let's anyway assume that these conditions are satisfied. Then what you see is that on the left side, at the EIT point, there is no output, whereas on the right side there is an output. So the coherent photons which you produce are now completely transformed into the signal on the other side. And what happens to the mechanical mode? Originally you had, let's say, this behavior of the mechanical mode. So with the other cavity, you get this. So the mechanical mode starts becoming dark because you are converting the mechanical mode to the signal on the other side. And so this process you can use for mode conversion, and this last part of the condition is difficult to satisfy, and that's why you never get this 100% conversion in the actual experiment. And just on the sideline, that this kind of effect is quite generic, and you can see it in other classes of systems. And so some of my colleagues who work on metamaterials, they could realize this in different kind of metamaterials with these dolmen structures, with these split ring resonators. Okay, so finally I'd like to discuss some of these quantum optical effects, and And as I said, that this long list is really a wish list. Um, you can you can introduce lots of theoretical ideas and you get lots of interesting results, but experimentally we are very far away, to get to study many of these quantum mechanical effects. All right. So Marlon, I have another 10 minutes or so. Okay. So one of the possibility that that we are very interested is to look at this what is called transduction of single photons, and the idea is the following, that you have here your red detuned laser and your signal beam. Let's assume that it's a single photon at this frequency. So this single photon combined with this via the optomechanical interaction would produce a single phonon, and this single phonon later, if you now switch off this your pumping field, and later within the coherence time of this phonon you bring in another field of frequency omega L prime, then you would have converted this single photon of frequency omega L to a single photon of this frequency. So you have gone from this to this frequency, and so that's what would be the transduction of single photons. Or you can also say this is like a state transfer. You transfer the state of a photon at this frequency to the state of a photon at this frequency. So such a state transfer has been demonstrated, but not with single photons, with very, very weak laser beams. And of course, one would like to do it with single photons. Okay, so the possibility of generating photon pairs using optomechanical interactions, and here I illustrate this possibility. Think of a double cavity system. Let's say one of the cavities is driven by a blue detuned laser, and the other cavity is driven by a red detuned laser. Or you can think of a silica resonator again, and you choose two different modes of the silica micro resonator. So that's equivalent to this again. Okay. So if we think of a blue photon here, so the blue photon would be at the cavity frequency plus the mechanical frequency, and this photon can generate a photon and a phonon, and there is some spread here. So little omega depends, gives the spread. The red driving, what it can do, it can take this phonon omega m minus omega, which you generate here, combined with this red driving, and produce a photon at this frequency omega c minus omega. So this way we have generated a photon pair. This one is omega c plus omega, this one is omega c minus omega. And this photon pair is entangled. And so if you look at this as a net effect of these two processes, This is the net effect, that you are coming with a blue photon and a red photon, and via this optomechanical interaction you produce these two photons which are in the vicinity of the cavity frequency, one on one side, the other on the other side, and so this interaction becomes equivalent to this kind of an interaction, which is the standard down conversion interaction in quantum optics. However, the difference is that in the standard nonlinear crystal, this is kind of a passive interaction, whereas in our case, this is a active interaction. So we can generate photon pairs, and so we can generate squeezing, the squeezing of the radiation field, and at zero temperature we can generate quite substantial squeezing, but since zero temperature is very difficult to reach, so this squeezing gets quickly degraded by the thermal effect. Even few phonons destroy the squeezing. Okay, the other question is that can we squeeze the mechanical oscillator, and that's little more difficult to do. And one of the ideas that we introduced, we thought that we put in the cavity a parametric amplifier. So we add a parametric amplifier in the cavity, and the idea was that the parametric amplifier in the cavity will squeeze the cavity photons, and if somehow we can transfer this squeezing from the cavity photons to the mirror, then we can squeeze the mirror. And it turns out that it works, that the squeezing of the cavity field, which is produced by this parametric amplifier, can be transferred to the mirror via optomechanical coupling, and therefore the mirror can be squeezed. And well, the transfer of the quantum state of the cavity to the mirror is used. The degree of the mechanical squeezing is limited by the squeezing produced by the parametric amplifier, and we know that the parametric amplifier can produce only 3 dB squeezing inside the cavity, and so the squeezing of the optomechanical mirror is limited by 3 dB, but we can increase this by using the other tricks like quadrature feedback scheme, and that way we can substantially increase the mirror squeezing to more than 50%. The squeezing of the mirror can be detected by squeezing of the output field by choosing parameters for which output shows no squeezing if mirror motion is unsqueezed. So we work on the parameter regime where the output will not show any squeezing if the mirror is not squeezed. And so if you find that the output is squeezed, that's an evidence that the mirror is squeezed. We always get the indirect information about the mirror by looking at the output. Now, Frost group in Caltech, they reported squeezing of the mechanical mirror, and they used slightly different mechanism. They did not put a parametric amplifier in the cavity. They used both blue and the red detuned drives on the cavity, and the application of both blue and red detuned drives sort of simulates a parametric interaction inside the cavity, similar to putting a parametric amplifier. And what they reported about 1 dB of squeezing for the mirror, and this was a low temperature system, and so their temperature was like 10 millikelvin, but even at 10 millikelvin they had large number of the thermal phonons, which is due to this small frequency of the mechanical mirror. So the limitation is basically this number of the thermal phonons. That's how they detected only 1 dB of squeezing. Okay, so quadratic coupling, I'll leave it out. Well, optomechanical systems are beginning to be studied for collective effects involving several mechanical oscillators coupled to a common cavity. So one can in principle study super radiance like effect or the collective gain effect, and the kind of, there are already systems where people are studying several mirrors, and particularly the electromechanical systems. So this group earlier studied several mechanical mirrors. So each of these capacitors in the electromechanical system behaves like a mirror where these plates are movable, and that's what gives rise to electromechanical interaction. All right. So as far as the quantum effects are concerned, there is considerable progress on the experimental side, but again the limitations is due to the thermal phonons. And what we have so far reported, we have done everything in what's called the linearized treatment of quantum fluctuations. And in principle, one needs to go beyond the linearized treatment of the quantum fluctuations. As the quantum fluctuations become larger and larger, then this linearized approximation would not work. We have treated the mirror as a linear harmonic oscillator, but in principle one should account for the intrinsic nonlinearity of the nanomirror. So we have to include the anharmonicity of the nanomirror. And lastly, these are the topics where currently a lot of interest in coupling the nanomechanical system to atoms, to plasmonic systems. And so here are the conclusions. I didn't have time to talk about issues like the force sensitivity. That's where a lot of interest is there. And it turns out that if you put a parametric amplifier in the cavity, which produces squeezing of the mirror, then you can beat the standard quantum noise limit. There is also possibility of a variety of two-phonon processes in optomechanical systems, and I didn't have time to talk about these. So thank you for your attention. Right. Right. Yeah, there is indeed. So what is the question? Okay. Okay, so he's saying maybe I need to go back. Okay, so I showed these in an optomechanical system, the dressed modes, the real and imaginary part, and he is asking about this point. So this point is known as the exceptional point. And what happens at the exceptional point? This is from the mathematics side, that a resonance, a pole which is of first order becomes a pole of second order. Okay. Now this pole of second order has consequences. If you look at this, for example, time dependent behavior, a system which is decaying, for example, exponentially, if you have a pole of second order, then you get a time dependence like t times e to the power minus something. Okay. So in the spectrum, if we are looking at the spectrum, then the effect is just that the pole changes from first order to second order. And so anytime we have a resonance which is second order, it looks narrower, by roughly a factor of square root of 2. Okay. Yeah. Yeah. Well, the modes which we look at in membrane, these are basically collective modes, of the system, like a center of mass mode. So that's what one is looking at, and the interaction with the light fields.
Could we go back to the superfluid helium experiment?
Oh, I don't have their experimental picture, but basically it's like the fluid system is in a fiber cavity. So they design a fiber cavity and put the fluid inside the fiber cavity.
So they're relying on some sort of coupling between the fluid and the walls of the fiber.
It is the coupling between the fluid and the field which is inside the fiber.
So index of refraction?
Yeah, basically index of refraction. Now see, if you look at this one, so this extra term, basically this is the dielectric function or the index of refraction for the superfluid, which is a function of this density rho. And so in the interaction term here, you get the d epsilon by d rho changes in the dielectric properties as the density changes. It's coupled to the optical properties of the superfluid. Yeah. Yeah, so in this case, the optomechanical interaction, the origin is not the motion of the mirror. The optomechanical interaction is due to the motion of this fluid which is inside the cavity. Okay, so it's a different mechanism, but it gives you a similar kind of optomechanical interaction. So you are talking of motion of the fluid or the phonons in the fluid which are interacting with the light fields.
Thank you.
Yes, thank you.